Okay. Al-Khwarizmi Abu Jafar Muhammad ibn Musa Al-Khwarizmi's life. I'm going to call him Al from now on, just because that's a mouthful. So, so we don't know a lot about him. In fact, we know really very little for about one of the fathers of algebra. He's foundational to the algebra that you guys have all used and most students use. He genuinely set the stage, though notational he did not, right? His stuff was all words, he wrote it all out. So an unfortunate effect of this lack of knowledge seems to be the temptation to make guesses on very little evidence. There are people who could decipher his name somewhat. Muhammad is from the Prophet Muhammad, and Ibn Musa is usually son of, sort of thing. So, but the Abu Jafar, I don't know how those translate. And the problem with, not the problem, Arabic names have meanings. Each word means something, and it could be about strength or rivers or whatever. So we don't know a whole lot. Here's what we do know. We do know that he was invited to come to Baghdad around 820 during the reign of the Caliph Al-Mamun, and he spent the rest of his life there under the patronage of that caliph and his successors. His most famous book, Hisab Algebra wa al-Muqabala, which is translates into Compendium on Calculations by Restoration and Reduction. As his most famous book, this is where we get most of what you guys know and we know of algebra in the foundational sense. And algebra sounds familiar. It should, because it is a mistranslation. It's how we get the word algebra. He doesn't use symbolic expressions, all expressed verbally and or geometrically, though I'm going to use what we're familiar with as far as algebraic notation in this presentation, just to help us understand. He did not. He would never have written 1 0. He wouldn't have written that. He just wouldn't have. He would have said 10 of something. And it would have been in words. So keep that in mind as we continue. Come on. He gave general methods for solving quadratic equations, other types of solving methods and manipulations, beyond any previous work that we know of in some cases. Some cases we know had already been done before. He was a scholar in the House of Wisdom. So this means he had access to the great works that predate everything that had been compiled up to the Library of Alexandria, and then those that survived the Library of Alexandria's destruction that actually ended up in the House of Wisdom. So he had access to all that. Euclid's Elements, tons of other works. So, and again, we're talking about this book like it's a book. It's not, right? No physical book. These are scrolls. These are compiled scrolls of his work. He compiled it to sell it, to put it all together in one place. He didn't compile it to sell it. He didn't compile it to make money off his work. He was a mathematician. He was more concerned with having something that was detailed. His equations for linear or quadratic are composed of the idea of units, roots, squares. We would call these as radicals now, but squares. He was using the term squares very generally. In fact, most of them were squares, but not necessarily. So for example, to Al-Khwarizmi, a unit was a number. A unit of 4, a unit of 25 units, 4 units, 6 units, whatever it may be, okay? A root was this unknown. It was x, though he would not have used x. 1, x, it wasn't in their language, isn't in their language, so it would not have been used. And a square was this unknown to the power of 2. I am using the x, and I'm using that because we write in English, and we're using that, and you guys are used to that, but that's not the symbols he would have used. The Hisab, Algebra, Al-Maqabala was not completely pure mathematics, though, as we think of pure mathematics now. So this looks at rules for finding the area of figures, such as circles, also finding the volume of solids from spheres, cones, and pyramids. His section on mensurations, which is measuring of geometric magnitudes, lengths, areas, volumes, etc., certainly was more comprehensive and more in common with Hindu and Hebrew texts than any Greek work. It isn't that he didn't have access to the Greek work. Again, everything that was translated from by Arabic scholars and Islamic scholars in the time of Alexandria end up in the House of Wisdom, which is the, let's call it the capital of the Islamic Empire at the time. Though capital is more like the, yeah, that's as good a word as any. He was very familiar with Hindu and Hebrew texts. So those had more to do with it than the Greek texts. He was aware of Pythagoras' theorem and Thales' work. Thales arguably was writing in something very probably what we would call Greek in general. And then also he had an extensive section on solving problems about questions of distributions of bequests in wills and inheritance, which is a very big subject in Islamic law. It's all predetermined and involves a lot. It involves pretty extensive and intricate computation with fractions, though they were written out, right? The reduction is carried out using the two operations of algebra and al-Maqabala. Here, algebra means completion and is the process of removing negative terms from an equation. It is where we get the word algebra from, and it's restoration, and equivalence. For example, using one of Al-Khwarizmi's own examples, algebra transforms x squared equals 40x minus 4x squared into 5x squared equals 40x. So on the, and I guess this on the thing scrolls over, but we're talking about this. 40x minus 4x squared. And the idea of what I would call, maybe we call this isolating. He looked at it as removing negative terms. So wherever the negative is, he's going to try to move it so we have things that are positive. And the term al-Maqabala means balancing and is the process of reducing positive terms of the same power when they occur on both sides of an equation. For example, here's an example that reduces 50 plus 3x plus x squared equals 29 plus 10x to 21 plus x squared equal to 7x. One application to deal with the numbers and a second to deal with the roots. Okay. He uses both of these algebraic, what we would now call algebraic methods of solution and geometric methods. How can we solve a quadratic equation geometrically? Most of you know completing the square, factoring, the quadratic formula. Okay, those are your big ones to do them. Factoring, obviously, usually the quickest. Not obviously, it's usually the quickest. Quadratic formula only forces you to, you could look at it as through, I think of it as the quadratic formula forces you to factor through completing the square, which I know feels weird to say, but every formula only works because it forces you to do a method that always works. Not because the formula always works. The formula is a tool. And how you think of the quadratic formula is not how he thought of it. So we're clear, the quadratic formula is maybe 100 and something years old, not old. The quadratic formula prior to that students would learn in the 1800s, early 1800s, goes back about 1,000 years. So your quadratic formula that you guys use is new. It's a new creation. Was it very different? Well, it actually looks pretty substantially different, though the actions that happen are the same. So let's look at this quadratic formula, the quadratic equation. So here's the example. This is to solve this equation, x squared plus 10x equals 39. And I put that he writes, but let's be honest, he didn't write in English, and so this is all translated, and I use symbols just to make everything fit. He would not have done that. So a square and 10 roots, right? This is a square, 10 roots, are equal to 39 units, right? So that's that piece, this piece, and that piece. I want to make sure you see it and you know where it comes from. The question, therefore, in this type of equation is about as follows. What is the square which combined with 10 of its roots will give us sum total of 39? The manner of solving this type of equation is to take 1/2 of the roots just mentioned. Now the roots in the problem before us are 10, therefore take 5, which multiplied by itself gives 25, an amount which you add to 39, giving 64. Having taken then the square root of this, which is 8, subtract from it half the roots, 5, leaving 3. The number 3, therefore, and I didn't transfer that, oops. The number 3, therefore, represents one root of this square, which itself, of course, is 9. 9, therefore, gives the square. So he determined that x is equal to 3. And he'd be right. That's not up for debate. It's just the process, right? So what does this say? If we're doing calculations, because that's what we tend to like to do, what did this say? This said x squared plus 10x equals 39. And then it says, okay, half of the 10, so half of this, and what would this be? So let's think about this. A, if we were thinking like we think of quadratics, A equals 1, B equals 10, and C equals 39. So I'm taking half of B, halves, and then I'm going to square it, right? It tells me to square it right here, which multiplied by itself. So I'm going to do this. And some of you may know, hey, that looks like we're finding a vertex, or like we're completing the square, and this is very true. So then we would add 25 over here. This is all he does. He doesn't add it to both sides. He adds it here. So he gets 5 halves, or 10 halves squared, which is going to equal 5, and then he squares it 5, right? So he does this, and he says this is x squared plus 10x. I'm going to keep that all like it was. And now I have 64. And if I take the square root of 64, all right, square root of 64 is indeed 8. I take away this half, right? So I take away this. So to that I'm going to minus 5. And this is indeed 3. Therefore, x equals 3. The number 3 therefore represents one root of this square. And this piece is just, which would be 9. Pretty straightforward. So this is, sorry, this is a geometric. So by completing the square, following what he said, so we had x squared, and we have these roots, and we know that the roots are 10. So, since this root here and this root here should be 10, the two together, that makes each one of the, or the 4, right? Because there's one here and one here. So we say, okay, well, what's half of that? Half of that's, they're 10, so half of that is 5. Cut them in half. So this root here and here, if I add them together, I would get 10 halves, 10x half, right? And if I cut that in half, that would be 5. But if I add this and this, I would have 20. So I would have 20 x over 2, which would be 10x, right? So Al-Khwarizmi starts with a representation with a square, and the side lengths are x. So that's this on each side, which then would represent this area. And he says, okay, now if I want to sum it all up, and he puts it together like this, and I'm going to take it a little bit farther out for a reason, and he says this is everything I have, but I want it to equal 39, right? I want all of that to equal 39. So what must be added over here? So to the square, he adds the 10x, and this is done by adding the 4 rectangles, each of a breadth of 10/4 and a length of x, right? And 10/4 would simplify to be 5 halves. So this is just what this is, right? And to the figure that has this area, which is equal to 39, you'll notice that 39 is the shaded area. We complete the square by adding the 4 little pieces. Well, we know that they're 10/4, right? That this piece here, this length is x. This length is 10/4. Well, if I cut that in half, or if I just consider, well, what is this, right? Let's simplify it. This is 5 halves. And if I have a square that is 5 half by 5 halves, what do I have? I have a square that is 25/4. Okay? Hence, outside the square in the figure has an area of 4 of these. 25/4 plus 25/4 plus 25/4 plus 25/4. Again, common denominator, we're adding them all up. This becomes 100/4, which cleans up to be 25. which we would add, right? We basically would add 4 times the 25 fourths to our 39, which would be 25, added to the 39, which is 64. The side of the square is therefore 8, but the side is of length 5 halves plus x plus 5 halves. So x plus 5, so we're going to subtract 5, right? So, because we have the 5 halves. This side is 5 halves, right? We found it over here, but it's the same piece. So if this is 5 halves, and this is 5 halves, and this is x, we have 5 halves plus. So 5 halves plus x plus 5 halves, which becomes 5 plus x, because 5 halves plus 5 halves is 10 halves, which simplifies to be 5. So x plus 5 equals 8. We're going to minus 5 from both sides, and x is therefore going to equal 3. That is the process. His process is completing the square. He thought of it geometrically, not algebraically. Though his thinking of it geometrically gets transferred to become the algebraic way of solving it, which is kind of cool. It's a funny thing how words work. He also wrote a treatise on Hindu-Arabic numerals that would later be read by Leonardo, that would help to bring it here to Europe, or bring it to Europe, which would then transfer to us. The Arabic text is lost, but the Latin translation, Algoritmia de Numero Indorum, in English, Al-Khwarizmi on the Hindu art of reckoning. So that's Latin, right? Latin here, English, this is what we call it. Gave rise to the word algorithm from this. This is the Latin translation of Al-Khwarizmi's name. So his name gives us algorithm. The name of his one book gives us algebra. So all of this is really happening. The Latin translation, which has been translated in English, is known to have been changed from Al-Khwarizmi's original text, and of which we don't even really know the original title. The work describes the Hindu place value system. So this is often called the Hindu-Arabic, but Idru Hindu is a better choice. This is all the Hindu people, Indian, from India, Indian. So it is all from there. And this is the first use of 0 as a placeholder in positional base notation. This is where we first see it. It'll get translated or transferred to the medieval, or not medieval, but the European, probably about the end of the medieval time period, which we're talking about now. It's by the time the Renaissance starts, we're using it in full swing. Methods of arithmetical calculations are given, and a method to find square roots is known to have been in the Arabic original, although it was missing from the Latin version, most likely because the Latin version was very strong in the Catholic Church, and anything that might have been a problem or caused a problem with the belief that the earth is the center of everything. Everything else God created doesn't matter as long as it's here in earth, sort of idea. And they weren't sure. I think genuinely it was more of a we're not sure sort of situation, so they left it out. The Indian text on which Al-Khwarizmi based his treatise was one which had been given to the court of Baghdad around 770 as a gift from an Indian political mission. So remember, Baghdad is the central hub. You have people coming there with gifts of knowledge, and because the caliphs, not just Mamun, but others before him, Harun and stuff, were very and I don't want to say hungry for knowledge, but desirous of it. They thought it was important to become educated. And so they were getting stuff from China and other countries towards the east that the Greeks had not gotten. So, and they, of course, were still getting stuff from the Greeks, from Romans and the medieval Europe, Turkey, all of that. So they were getting a lot of stuff. He wrote a major work on geography called Sintian Zij. I'm probably pronouncing these wrong. I'm just trying to give my best. This gives latitudes and longitudes for 2,402 locales as a basis for a world map. And the book is based on Ptolemy's geography. His list with latitudes and longitudes, cities, mountains, seas, islands, geographical rivers, and regions. And the manuscript includes maps, which on the whole are more accurate than those of Ptolemy. Remember, Ptolemy was in Alexandria, so he was in northern Egypt, but had not visited as many places as Al, and had not had as much contact with as many places as people who have come to Baghdad. So it's clear that where the more local knowledge was available to Al-Khwarizmi, such as the regions of Islam, Africa, and the Far East, his work is considerably more accurate than that of Ptolemy. But for Europe, Al-Khwarizmi seemed to have used pretty much everything Ptolemy had, because he'd never explored or had connections with people from Europe. A number of minor works were written by Al on the topics such as the astrolabe, on which he wrote 2 works, on the sundial, and on the Jewish calendar. Again, he was Islamic, but he was familiar with both the Hebrew and Jewish calendars. He also wrote a political history containing horoscopes of prominent people, basically talking about their birth year and then their implied years of doing stuff that's major. And we'll stop here. I'll pick up on some of the others in the next one.